Okay, I'll wait a minute or two. I don't know about you guys, but I need a spring break. Good news is that I just got my second vaccination yesterday. So by the time spring break is over, it'll have been 10 days, more than 10 days. So I'll be clear to do whatever. But anyway, I don't know if today we'll go the full 2 hours. We'll see. How many people we have? We wait for a few more people to show up. Since I was talking about the vaccine, you know, this whole thing, there's this joke I've been telling. The whole thing started with a virus from a bat. And so what do you bring in to deal with a bat? Well, you bring in the Joker. And that got me thinking of the Heath Ledger Joker. And I started doing this thing like, all these people, they said the bat would save you, that the bat would save your lives. But it wasn't the bat that saved you, was it? No, it was the scientists. It was the people like me. They killed the bat. They stopped the bat. But they think I'm a joker, but the scientists, we stopped the bat. Anyway, okay, I guess that wasn't as good as I thought it would be. How many people do we have at this point? 7 students. We'll wait for a couple more. It frankly is pretty amazing to live in a world where a pandemic could have an effective vaccination made in less than a year, validated in just under a year, and widely distributed probably, well, by a year and a half. I would say it'll be pretty widely, not fully, but pretty widely distributed. Oh, you like the Heath Ledger Joker impression? I don't know. I prefer the Joaquin Phoenix Joker. How about another joke, Murray? Oh, Murray. All right, how many people we have at this point? We've got 8 students. Okay, so last time we were talking about interference of waves. And today we're going to do some more cases that will build up to where we want to be with lenses right after the break. What we had done was the case of 2 small slits, and we found that they produced an interference pattern that oscillated up and down. And if the slits were separated by a distance d, then this was going to be, we were going to have cosine of kd sine theta would be the field, because we add up something from here and something from there. And so we've got e to the I k r, r1, should say be proportional to that, e to the I k r1 plus e to the I k r2. And I could factor out an e to the I k r1. All right, so it's really e to 1 plus e to the I k delta r. So we get, that's what the field is. Then the intensity is E star E which is going to be e to the minus I k r1 times 1 plus e to the minus I k delta r times e to the I k r1, 1 plus e to the I k delta r. These will just multiply out to 1. And when we multiply these, we get a 1. When we multiply these, we get a 1. And so we're left with 1 plus e to the I k delta r plus e to the minus I k delta r, or 2 times 1 plus cosine of k delta r. And this was wrong here. Let's just pretend I never wrote that. All right, that will be what the intensity is proportional to. And it has a peak right in the center where if we just did geometrical optics, you would think that all we have is a shadow. And it has zeros whenever k delta r is equal to pi, 3 pi, etc. So that we have an odd number of cycles. And so delta r over 2 pi delta r over lambda equals an integer plus a half times 2 pi. We can cancel out the 2 pi's. And delta r is d sine theta, approximately. So we get d sine theta over lambda equals m plus a half, or sine theta equals m plus a half times lambda over d. That's what we derived on Tuesday. And the key things to take away were, well, it predicts a peak at theta equals 0. And it predicts these nodes that get farther apart as d gets smaller, meaning that the light is spread out more, and they get closer together as d is bigger. And all of this qualitatively matches the trends we found in Zmax when we just played with the size of a lens and looked at how the light was smeared out. Any questions on that before we move to new things? Okay, then let's talk about the finite size of the slits. We were treating these things as very tiny, so tiny that if I were to draw a line from the top of the slit to wherever we're doing our detection, and another line from the bottom of the slit to wherever we're doing our detection, these two lines would be, if not exactly the same, then at least close. But we know that in reality, they're not exactly the same. And oftentimes, things that people could actually make, you will find that the slits are substantially larger than the wavelength of light. And all of these optical effects are going to be most visible when it's at least, when all these wave effects, excuse me, are most apparent when it's close to the wavelength of light. So let's start by just talking about what happens if we have one slit, right? And we're just going to figure out what would its pattern look like. So I will draw an axis here for simplicity. We'll put a detector here. We'll say that the height of this is d. So here's y equals d over 2. Here's y equals minus d over 2. And we're just going to look at some arbitrary angle theta, and we'll be adding up contributions from every point on there. All right, so we're going to add up a contribution from here and here and here and here and here and everywhere along there. We're going to add up contributions from each and every point on that aperture, because effectively that's what waves are. Waves are things that spread out from every point in space. There's something called the Huygens construction, where you look at a wavefront. So you look at, say, a series of points where the wave is everywhere in the space. A series of points, all of which have the wave at the same point in its cycle. And then you treat each point, excuse me, as an outgoing source of more waves. And at each point over here, I would just add up the wave from here and the wave from there and the wave from there and the wave from there. And that gives me the field here. And then I treat this point as a source of waves. And so you've got point after point after point after point radiating. It's a very confusing way to do calculations, but it provides a qualitative justification for the idea of basically just saying each of these is a point on here. I'm going to call this distance r, or r0. And then, of course, this path is a little bit shorter. And it's shorter by this amount. We're going to figure out what that is. We're going to take this little triangle here. This triangle has a height y. It's a right triangle. We're going to excerpt out that triangle. Yeah, I can do a better job than that. All right. So it's a right triangle. This is theta. This is y. This is 90 minus theta. So this is also theta. In this segment that we want, this is the difference in path length. Now it's opposite theta, and y is the hypotenuse. So this must be y sine theta. Any questions so far? So if our reference point at the center of the screen, the thing that we're measuring everything relative to, if that's producing a wave e to the I k r0 over r0, remember that that 1 over r0 just reflects the fact that it decays as it moves farther out. Then this one will be e to the I k r0 minus y sine theta over r0 minus y sine theta. And I could do that for every value of y. I could just calculate this thing here for each and every value of y, and we could add up all of those waves. And that's exactly what we're going to do. We're going to add up waves from all of the different positions along this opening, this aperture. Aperture being the technical term for an opening, coming from the same root word as abierto, Spanish for opening, because most scientific jargon either comes from Latin or Greek, and every so occasionally Arabic. All right, so we have to add all of those up. I am losing it. I think that first, that second dose of vaccine did have a little bit of an effect on me. All right, well, last time we talked about how if we've got this wave, that's the spherical wave spreading out, each of these points here is a point source. A small change in distance is not going to affect the denominator much, okay? Because if I change the distance by 10 to the minus 6 meters, right, but the total distance is 1 meter, well, that changes it by a millionth. On the other hand, changing by 10 to the minus 6 meters, comparable to the wavelength of light, could flip that oscillating exponential from pointing up +1 to pointing down -1. So we can have huge changes in the exponential from very small displacements, but essentially no change in the denominator, the 1/r, due to small displacements y. So I'm just going to write this as e to the I k r naught, e to the minus I k y sine theta over r naught. This is what it's approximately equal to. Any questions so far? Now we have to add all these up, and we're adding up over an infinite number of points. There's two ways to add up an infinite number of points. If the points have finite spacing, you do a sum. And if the points have infinitesimal spacing, you do an integral. Here we do an integral. So E's got to be proportional to the integral from y equals minus d over 2 to plus d over 2 of e to the minus I k y sine theta dy. Now you could fairly ask, why am I leaving this out? I'm leaving this out because it's the same everywhere. It doesn't depend on y. And when we multiply by it, it's just a constant factor out front. It's not equal to 0 anywhere. And what we're going to be ultimately trying to figure out is, what is the pattern? We're going to find that there's a pattern like this. And this constant factor out front doesn't do anything to help us figure out where are the peaks, where are the troughs. So we're going to mostly ignore this and just focus on this. Because usually what we're interested in optics is figuring out where the peaks are. You might think, well, don't we want to know how bright the peaks are? Well, we usually want to know how bright they are relative to each other. If I know that this peak is half the intensity of that peak or whatever, that's important to know. But the absolute intensity of the peaks is actually really difficult to calculate, not just because it involves some fancy integrals or whatever, but because it would also involve some knowledge about your equipment that's often hard to calibrate in absolute terms. Not impossible, but often challenging. And so we will just sort of say, okay, well, to really know what the absolute intensity is that we measure, we'd have to know a bunch of things about light sources, a bunch of things about detectors and filters. But if I know that this is 1/3 of this or whatever, then I can at least say that whatever this is, I can calibrate to what I measure there. That's the brightest thing. That would be the easiest thing to measure. So I could just calibrate to this and then just do the calculations that will tell me what's the value of this relative to that. So a lot of the times we just want to know where the peaks are, where the troughs are, and what their relative intensities are. And you did this integral on the homework assignment for today. You should get that it's e to the minus I k y sine theta over minus I k sine theta, evaluated from minus d over 2 to d over 2. So we're going to get, I'm going to put that minus sign up top. And the reason I want to put that minus sign up top is because it enables me to flip our limits of integration. All right. Multiplying the integral by -1 flips the limits. So then I have e to the I k d over 2 sine theta And it's I rather than minus I, because I got minus, minus. We subtract e to the minus I k d over 2 sine theta. We divide that by I k sine theta. Any questions so far? All right, well, I'm going to divide the denominator by 2 and multiply by 2. And I'm going to multiply the top by d, and I multiply the bottom by d. And the reason I'm going to do that is that then I can write it as 1 over kd sine theta over 2 times e to the I, this whole thing, minus e to the minus I, that whole thing. And now I've got e to the I something minus e to the negative I something over 2I. What's that?
It's 2I sine that mess.
Well, the top is 2I sine that mess, but then we divide by 2I, so we're just left with the sine of that mess. So we've got sine of this whole mess divided by this whole mess, which is something that shows up so frequently in optics and signal processing that it's got a name. It's called the sinc function. Because the sinc of x is defined as sine of x over x. And it shows up all the freaking time in signal processing, image processing, optics, you name it. And I had you plot the sinc function. And what you should have found on the homework is the sinc looks basically like this, and it decays away. Any questions? All right, that's how we handle a 1D aperture. But there are, most of the things that we deal with in optics are two-dimensional. Most of the time in optics, what we want to know is how to deal with something like this. I'm going to do the square and rectangular apertures today. And then on the first Tuesday after spring break, we'll talk about the circle. So the circle is obviously more relevant to lenses. All right, so here we've got our screen. We're going to detect light there. We've got some reference point. And our reference point will be in the center. And what we want to do right now is we want to figure out if I'm at a point R in this aperture. I've got XY coordinates in the aperture plane, okay? So I've got XY system in that plane. What I really want to know is what is this path difference here? And if we just ignore the fact that we're in some kind of tilted, that this whole thing is tilted, we would just say, well, you know, this path is still making an angle theta with respect to the center line. There is a center axis here. All right, it might not be, there's still a center axis. This path is still making an angle theta with respect to it. It might not be that that angle theta is directly above the horizontal, that we're just, when we go from the center axis to this red line, that we're going straight up through an angle theta. We may be going up and into the screen or whatever, but we're making an angle theta. And we still make that angle theta. And so our extra path is still equal to r sine theta, right? Where now r is the magnitude of this vector that goes from the center of our aperture to whatever point in the aperture we're currently looking at. And we're going to have to eventually integrate over all of the points in the aperture. All right. Now, this angle theta is a little bit unusual because theta is the angle between k, our k vector. K is going this way. It's the angle between k and the and this axis coming out of the plane. Now let's talk about the angle between k, the direction of the wave, and the position of this point in the plane, right? I'm gonna redraw some of this a bit larger. The center, here's our point R, here's the vector R to our point. Here's K. This is theta, then this is 90 minus theta. And I say that because this vector R is entirely in the plane, and this dashed axis is coming straight out of the aperture. R is in the plane of the aperture. The dashed line is straight out of the aperture. So let's see here, sine of theta. Well, how can I relate that to some trig function of 90 minus theta? It's cosine of 90 minus theta. So what I've got is, here's our path, r sine theta equals r cosine of 90 minus theta. We're going to be integrating e to the minus I kr cosine of 90, oops, that should be a 90 minus theta. Okay, we've got the length of the k vector, I'll write it like that. The length of the r vector, I'll write it like that. And this is the angle between them. Length of one vector, length of another vector, cosine of the angle between them. What's that? What's the product of all these operations? It's product of three things. What's the product of what we're doing here? Should be able to nail this one on the dot. What's this product?
Is it a dot product?
Yes, that was the whole thrust of my bad puns. All right. So what we've got is the integral over the entire aperture, e to the minus I k dot r. dx dy. Integral from minus, let's see here, x equals minus b over 2 to b over 2, y equals minus a over 2 to a over 2. I could rewrite that as double integral of e to the minus I kx times x, e to the minus I ky times y. And I should really do, what did I write up there? I want to stay consistent. Y went over, y went, okay, so that should be x equals minus a over 2. Y is minus b over 2 to b over 2. Well, this integrand is just a product of something that only depends on x and something that only depends on y. So we're just going to wind up getting product of two things that are exactly like what we had before. Oh, I left another d up there. This will be a sinc of kx a over 2, b sinc ky b over 2. Any questions so far? Let's pull out a Mathematica file. I posted one today. Posted a couple of Mathematica files for today. We want diffraction pattern of one slit. Should be available on Blackboard. Diffraction pattern, I actually posted it for Tuesday by mistake, but pull up diffraction pattern of one slit. And here's what you should find. We're plotting this as a function of angle. And I'm doing this for, here I tried something in the UV. Let's try something more smack in the middle of the visible range. So 0.55 microns. Remember to hit Shift Enter on this function definition. Then hit Shift Enter there. And I take this out to 5 microns. All right, I take this all the way out to 5 microns, meaning that I consider slit sizes from 0 to 5 microns. And we see that when it's 5 microns wide, we get a dip. Let's see, this is 20, so 15, 10, 5 degrees, a little bit past 5 degrees. Now, what if I made it 50 microns? roughly the size of a thin human hair. Human hairs vary in all sorts of ways, but roughly the size of a very thin human hair. Well, then I can no longer really see on this scale where the first dip is. So we'll narrow the scale. We'll go, instead of -5 to 50 degrees, we'll go go over a range of 5 degrees. Okay, so half a degree, roughly, because that's 1 degree there, so that's a half a degree. We would see that the light spread out over half a degree. But it would frankly be very difficult to make a slit that tiny with smooth edges. Rough edges create all sorts of additional scattering and problems. So instead of 50 microns, we'd probably be talking about 500 microns for anything that people once upon a time could have made with good reproducibility. So we would be talking about half a degree, probably. No, 0.05 degrees, a 20th of a degree, okay? If you made something that was half a millimeter in size, if you made a hole that was half a millimeter in size, and you just shined light through it, and you just want to see, hey, does the light spread out or not? Well, there'd be a few problems with doing that experiment. First of all, you'd have to send perfectly collimated light through it. And whoever made perfectly collimated light, okay? The only way to get to get really highly collimated light, frankly, the best source of highly collimated light once upon a time was sunlight. Or if you were to do something with a candle, you'd want to have a candle, put it very far away from a screen with a small hole in it. And the farther back the candle is, the more you know that all of the light that comes through that first hole will be going in pretty much the same direction. Then you put a second hole, a much smaller hole, even further past that. That would be a really hard experiment to do. And that second hole, if you were to make things reproducibly so that you could be reproducibly and measurably, would be about half a millimeter at most. And then you might notice that the light is spreading out by 0.05 degrees. And that would be a really difficult thing to measure. And I bring all of this up to explain why it is that it took people so long to figure out the wave theory of light. The ancients weren't stupid. The ancients did amazing things, right? The ancients figured out the math that we now know. It turns out, in fact, that there were predecessors to calculus. Although the really full formal development of calculus goes to Newton and Leibniz, the Babylonians had little bits and pieces of calculus in some of their work. People have unearthed tablets to show geometrical calculations that required them to know at least some amount of calculus. All right, Archimedes was a great experimentalist. The Greeks were amazing logicians and mathematicians. The Arab optical scientists were nothing to sneeze at 1,000 years ago. But in order to actually see the wave nature of light, you would need a highly collimated light source, and you would need to be able to make a very small aperture with sub-millimeter size, probably, or you can make something larger than a millimeter, but then you'd have to do, if we went out to say 5,000, let's make this 5,000 microns, okay? If we make this 5,000 microns, a few millimeters in size, then you need to be able to do angular measurements with a precision of 0.0005, 1/200th of a degree, which would have just been really incredibly difficult to do. And so the reason why the wave theory of light took so long, and the reason why, frankly, a lot of very practical optics is done without too much thought to the wave theory of light. Yes, every optical engineer knows the wave theory of light, but there's a whole lot of things that you can do without ever writing down a lambda in your calculations. It's because the kinds of angular spreading that, that wave optics gives rise to, for anything macroscopic, light hitting something macroscopic, those angles tend to be quite small. Any questions? This is why the Mesopotamians didn't do it. This is why Archimedes and the other Greeks didn't do it. This is why the Arabs of 1,000 years ago didn't do it. Frankly, as much as we scientists love to brag, as much as I was saying just a little while ago that it's great to live in an era where scientists can give us vaccines, scientists owe at least as much to craftsmen and engineers as technology owes to science. If people weren't able to do very precise machining to reliably and reproducibly manufacture and measure the sizes of very small parts, it would be much harder to have any confidence in wave optics. When you finally get to do in-person labs again, we're going to hand you things and we're going to say, oh, this slit has a 50 micron width and that slit has a 20 micron width. And you're going to take our word for it. And really, it's not even me you're trusting because I'm trusting the manufacturer. All right. The only way that any of these tests of wave optics have any reliability is that we have precision manufacturing. And yes, science has done a tremendous amount for precision manufacturing, but precision manufacturing has also done a tremendous amount for science. I don't think it's a coincidence that many key parts of the Industrial Revolution preceded modern physics rather than following it. Any questions so far?
Professor, I have a question. Slightly silly question, but so Young's double slit, I know it was like the experiment was conducted around the 1800s, early 1800s. How were they able to make the openings and slit that small back then?
I don't know half as much as I should know about the manufacturing, but I do know that at that point you were starting to see mass production of certain kinds of machine tools, mass production of pins and needles and small screws. And, you know, it's the things in life that you can get at a hardware store that make experimental physics possible. So I know that those kinds of experiments relied on the fact that you could get pins and needles and screws and nails with reproducible sizes. Otherwise, it would be much more difficult to measure tiny apertures. If all it took was brain power, believe me, every single intellectual feat we've achieved, the Mesopotamians were just as capable of it. In fact, if you really think about it, to go from simply speaking words to saying, let's make these marks on mud, and these marks will have meaning, and we'll assign logic and structure to these marks and rules and relationships for these little marks in mud. That's a leap. That must have been tremendously difficult. If you really think of the brain power it would have taken to do that, they could have done all of this if they had the technology, but it took precision machining to do this. One of my education on this actually came my freshman year of college when I got a job in a research lab. And the first thing they had me doing was machine drawing and designing parts for a machine shop. You can't build a scientific instrument without very well manufactured parts. Other questions? Well, then let's scroll down in that file. Now let's define this function, rectangular intensity profile. So you go there and you hit Shift Enter. Now I fix one of the dimensions. I'm fixing A. And A is for, don't know why I did that. Let's say that A is what we multiply kx by, and B is what we multiply ky by. All right, so I'm fixing A at 2, and we're going to vary B. What you should notice is that the larger we make B, the larger we make the vertical dimension, the smaller the diffraction pattern becomes vertically. If I make the vertical dimension really small, the diffraction pattern is really spread out vertically. So again, if the ancients could have made really tiny pinholes reliably, then they would have found very significant spreading of light. But when we make it large, then we find that the light spreads out very little in the vertical direction, which, besides explaining why the ancients couldn't do this, it also is once again reminiscent of what we found when we played around with Zmax. As long as we have a diffraction limited lens, the larger we make the lens opening, the smaller the spot size. Once it gets so large that it's aberration limited, then things turn around. But this helps explain why it is that when you're dealing with something diffraction limited, anything that you make, anytime you make the object small, the light gets spread out more, and vice versa. Questions on that? This phenomenon of physically large objects producing small diffraction patterns and small objects producing large diffraction patterns is why people who do diffraction experiments often speak in terms of something called reciprocal space variables, meaning that it's reciprocal, that the spacing of things in a diffraction pattern is inversely proportional to the spacing of things in the actual physical object, and vice versa. And that's why they talk about reciprocal space. There's a good, and we'll get the comments, a good YouTube video on the origins of precision made by machine thinking. Keith, could you elaborate on that? Because I haven't heard about that video, but I'm interested now. I'm going to look it up. Machine thinking, okay. YouTube machine thinking precision. Origins of precision. I'm not going to start playing it. I just wanted to find it and link it. One group of people who celebrated, remember a few years ago when they discovered gravitational waves? And this was sold as a very big deal for theoretical physics, fundamental physics, gravitational physics, because it proves Einstein right. It was sold as a very big deal for astrophysicists because they were looking at the merger of two black holes. But it was also a very big deal for optics people, to the point where the entire board of the Optical Society of America held a special meeting to watch the announcement, because it would be impossible to detect gravitational waves without high precision optics, to do interference experiments, having a wave bouncing back and forth between two mirrors. And if the path length between those two mirrors changes slightly, then the wave bouncing back and forth will interfere a bit differently. Okay, so I'm going to go back to my other device, and I want to say a little bit more about that. So we've shown that if we Fourier I'm about to use the word Fourier Transform. If we take the diffraction pattern of a single slit, we get this. and this spacing is proportional to lambda over d. And if we take the diffraction, measure the diffraction pattern of a rectangular aperture, we get something that looks like the opposite. It's narrow vertically, wide horizontally. So this diffraction pattern on the screen will be narrow horizontally and wide vertically. But we don't have to just take diffraction patterns of slits that are open. I mean, we've done the single 1D slit, we've done the rectangle. Next time we'll talk about the circle. You could say, hey, other shapes, why not do a triangle, a hexagon, or whatever? But there are more fun things that people can do. One thing you could do is you could put on some kind of mask with variable transmission. And if I took a side view of it from the side, it might look like some parts of it might be narrow. Some parts of it might be wide or wider or really narrow. Now, why on earth would we do that? Some parts of it may be dark or just a little bit dark. Well, the thickness would give us time delay, phase shift. And the opacity, if I were to make it only partly transmitting, would determine the amplitude, just how much light gets through. And I could decide, this is kind of a weird drawing of it, but basically I could make it a bunch of pixels, okay? Pixels of different thicknesses. And I could decide how reflective or transmissive or absorbing each pixel is. And I could decide exactly how much delay the wave gets going through each part. And now what I'm doing is I'm adding up a whole bunch of waves with different phases. And I can then control what I get. I could add up all of these waves on a screen over here, and I could get any kind of pattern I want from that. Now, the mathematical theory behind that is, well, let's see here. I'm calculating an integral over an aperture of e to the I kx times x, should be e to the minus I ky times y, dx dy, and I'm multiplying it by some function t of x, y. T just stands for transmittance. And t could be between, the absolute value of t is between 0 and 1. And the phase is between 0 and 2 pi. It just depends on how much delay I put in the way. Now, I don't know what that idiot who taught math methods last semester did. Did he ever tell you about Fourier transforms? Hopefully. Well, whenever you've got a function multiplied by e to the plus or minus I times k times whatever variable the function depends on, we have a Fourier transform. So what we've got here is that this diffraction pattern is equal to the Fourier transform of our transmittance function. And we can Fourier transform almost anything. And we can inverse Fourier transform almost anything. So you tell me what pattern you want here. Make any messy function we want. You tell me what pattern you want here. And we can Fourier transform that, or inverse Fourier transform that, and figure out what this should be. And once we know what this should be, then we just shine light on it. And the diffraction pattern will be the Fourier transform. So we have our aperture opening with a transmittance T of X, Y. That gives us our diffraction pattern. But the aperture is just the inverse FT, the inverse Fourier transform of the diffraction pattern. And this is how people design holograms. This is how people design optical traps. This is how people design a lot of the things in laser light shows. Have you seen, it was big a few years ago, my nephews got these Christmas toys that you shine a laser pointer on them and they make this pattern that looks like a bunch of Christmas trees. You could make, it didn't have to be a Christmas tree, but whatever. You just shine a laser pointer on it and you can make something that looks like whatever you want it to look like, whatever the designer made it. Somebody said, okay, let's take a picture of Santa Claus or a picture of a Christmas tree, or if you wanted to make it as an accessory for a movie, a picture of whatever cartoon character you're trying to sell merchandise of, and let's inverse transform it. And that will tell us exactly how transmissive this aperture needs to be. And then we will shine a laser on it, and that Fourier transforms it, and we will get back the Christmas tree or Santa Claus or the movie character or whatever. That's the idea. A diffraction pattern is just a Fourier transform. So when we deal with a lens, we are really, let me do it this way. If I have a point here, in principle, everything should go forward. In practice, it spreads out. How it spreads out is proportional to the Fourier transform of a circular aperture. Now, don't worry, I'm not going to test you on the Fourier transform stuff because math methods isn't a prereq for this class, and there are a couple of people in here who I didn't see in math methods last semester. For those of you who've already studied Fourier transforms, this is one reason why they matter. For those of you who have not yet taken math methods but will, this is one reason why Fourier transforms will be important. Any questions? Then I want to talk about two more things. I want to go back from, I've been giving you a very general picture here. We'll return to this. So next week, well, not next week, the week after spring break, we're going to deal with lenses and their diffraction limit and how that limits the information you pull out of them. Then we're going to talk about thin films for about a week and a half and diffraction gratings. Somewhere in there, we're going to talk about how the diffraction limit affects microscope performance and read a paper on designing special lenses to improve microscope performance. So tie together all the lens stuff we did with the diffraction physics that we're doing. Then we'll get to diffraction gratings and return to some of those Fourier ideas. But let's talk about the two-slit experiment now. Okay. Let's talk about the real two-slit experiment, where we no longer assume that the width of these apertures is just infinitesimal. We'll call the spacing between the centers D. And we'll call this width A, right? So here's y equals 0. Here is y equals, let's see here, d over 2 minus a over 2. Then this would be y equals d over 2 plus a over 2. Here would be y equals minus d over 2 plus a over 2. And here would be y equals minus d over 2 minus a over 2. All right, those are all of the coordinates, because here's d over 2 minus d over 2. These are the centers of the slits, and then in each case we're either going a over 2 above or a over 2 below. So there's two ways that we could deal with this. One is we could just, well, we'll still consider a reference path from the center. We're going to have a screen over here, and we're going to detect light wherever on that screen. And we could do it a couple of ways. One thing we could do is we could just integrate from y equals minus d over 2 minus a over 2 to y equals plus d over 2 plus a over 2. Some transmittance function of y that's 0 here, 1 there, and 1 there. We still need theta. Right, that would be one way to do it. But that would still, in the end, require us in practice to do two integrals. So we'll write out each of those integrals. We're going to have an integral from d over 2 minus a over 2, d over 2 plus a over 2, e to the minus I k y sine theta dy. Then we're going to have another integral over the bottom slit. Right, we could do that. Now, I want to show you a way of breaking this up a bit further. We've already broken it up into two integrals. But what I'm going to do is, on top, I'm going to say that y equals d over 2 plus u, where u is some variable that goes between plus or minus a over 2. And down here, I'm going to say y equals minus d over 2 plus v, where v is again between plus or minus a over 2. And of course, dy will just be du. Down here, dy will just be dv. Well, now I'm not integrating from d over 2 plus minus something to d over 2 plus something. I'm just integrating over u values or v values. So I could rewrite this as an integral from u equals minus a over 2 to u equals plus a over 2, e to the minus I k d over 2 sine theta, e to the minus I k u sine theta du, plus an integral from v equals minus a over 2 to plus a over 2, e to the minus I k times negative d over 2, I should have written du there, my bad. Well, let's see, I can't pull out anything that depends on u. If there's any factor or term in this integrand that depends on u, I have to leave it in there, but this doesn't depend on u, and this doesn't depend on v. And come to think of it, if I pull those out, then I'm just left with the same integral, all right? And I have e to the minus I k d over 2 sine theta, integral from minus a over 2 to a over 2, e to the minus I k u sine theta du, plus e to the I k d over 2 sine theta, integral of the same thing again. Okay. So the same integral, just these two different factors here. And e to the minus I something plus e to the plus I something, what's that?
Just 1.
No, if they were multiplied by each other, it would be 1. When I add them, if I had e to the ix plus e to the minus ix, 2 cosine of x. So it looks to me like I've got 2 cosine of kd over 2 sine theta times sinc ka over 2 sine theta, and there should be an a in there as well. Now I broke it up this way and went through all of these tedious things because suppose we had not just had some simple transparent slit there and there. We'd had something more complicated, some really messy phase mask with whatever pattern of delays, phase shifts, and changes to transmittance, whatever messy thing you want. But whatever messy thing we have up here, we have the exact same messy thing down there. Then what we would have is 2 cosine kd over 2 sine theta times whatever the diffraction pattern of one slit would be, right? And if I had 3 slits, 3 identical slits, then whatever the messy pattern, there's no guarantee that this slit is anything nice and simple, but whatever it might be, I'll just call this Y1, Y2, and Y3. We would have the one slit pattern multiplied by e to the I k minus I k, y1 sine theta plus e to the minus I k y2 sine theta plus e to the minus I k y3 sine theta, and so forth. It would be similar if we had 4 slits. We just add one more exponential in here. If we had 5 slits, we'd add 2 more. This is something that happens a lot in diffraction theory. If you have some identical element repeated over and over again, you can factor the diffraction pattern into the one slit part and something that depends on how the slits are distributed. And this is called, in some communities, the jargon is form factor and structure factor. Other subfields will have a different name for it, but what's in the name? That which we call a rose by any other name would still smell as sweet. It's all the same idea. Whenever you have these repeating elements, you can factor it. And this is, anybody think of a situation that involves diffraction of electromagnetic waves from a bunch of repeated units? Crystallography. You have a crystal, it's just a periodic arrangement of atoms, and you shine things on it, you shine electromagnetic waves. Now, those electromagnetic waves aren't going to see anything if the wavelength isn't comparable to the spacing between the atom. So you do this with X-rays, you shine X-rays onto a crystal, and you will get some complicated pattern that will depend on the diffraction pattern of maybe not one atom, but if these are a periodic arrangement of molecules, whatever the pattern of that one molecule is. And then something that depends on how the molecules are spaced apart. This is really important in biology. They crystallize proteins to figure out the structure of the protein. So they will basically just, it's not a sinc function because we're no longer talking about the diffraction pattern of a slit. It's something much messier, but still, they can look at that and figure out what this form factor is, separate out the structure factor, and then kind of work backwards to figure out what the distribution of atoms is. And that's how they figure out the structure of protein molecules. Any questions? You should not be at all surprised that last March, when most of us had to go home and a whole bunch of people could not continue working in labs, protein crystallographers wound up working more hours rather than fewer, because biology research kicked into high gear, and anyone who was doing protein crystallography on anything even vaguely related to COVID, they were deemed very, very, very essential workers. And I don't think that they have caught any sleep in the past year. Any questions? Let's go back into Mathematica. Let's open the diffraction pattern of two slits. Whenever I open a new Mathematica file, I always first close Mathematica just so that it forgets any definitions it was previously using. If I'm using the same variable name to refer to a slightly different physical concept in the new case, then I don't want to have to deal with that. And what is my computer doing? Can you guys hear me?
Yeah, we can hear you.
Yep.
Okay, my monitor just did something weird. So I have a 2 monitor setup and one of them is misbehaving. So I lost Zoom, or I lost my site of Zoom, but I didn't lose my microphone. Okay. All right, looks like my other monitor is back. That, the other screen. Okay, so let's share my screen. All right. So, diffraction pattern of 2 narrow slits, the thing that we did last time. We can play with this. Here I fixed the wavelength at 0.5 micron, so blue-green light. You can play with what angle we let it go out to. And it does decay very slowly as you go away from theta equals 0, just because as you go much further up on the screen, you're going much further away. And so that 1/r term is going to become smaller. That 1/r factor, I should say. Then we consider 2 finite slits. So now we've got K, which involves the wavelength, the angle, the slit separation, and the slit size. And now we have 3 things that we can play with. We can play with the slit separation, the slit size, and theta max. And what I want you to notice is that when we play with the slit size, it doesn't affect the small scale features. Okay, the slit spacing is what determines the small slit scale features. If I make the slits really close together, you see how these little ripples get really fine. If I move the slits farther apart, the underlying, the smaller peaks get a little bit wider, a little bit farther apart from each other, but not that much farther apart, okay? They're still much tinier. Whereas if I play with the slit size, that determines where these secondary peaks go. And if I can even see the third peak, there's the central peak, the secondary peak, you can kind of just barely see the secondary peak. And I could justify this in 2 ways. One would be to just say, well, you know, this is what we calculated, all right? That's one way to do it. But then the other way is to say that whenever you take a diffraction pattern, anything that's very large in physical space gives rise to very small features in the diffraction pattern. Hence, the ancients couldn't know wave optics because everything that they were able to reliably and reproducibly make would be much larger than the wavelength of light. It would just give rise to very, very tiny, hard to make out features in the diffraction pattern. Whereas anything small, like the size of the slits as opposed to the separation of the slits, the small scale features give rise to the large scale, things that are physically small give rise to the large features of the diffraction pattern. That's what I want you to take away from this. Any questions? Okay, so today's key lessons. Once again, we keep on finding that anytime we calculate a diffraction pattern, we always get a bright central peak as opposed to a shadow in the middle. That's consistent with the lessons of Poisson's spot and Young's two-slit experiment. We keep getting that, just like the lens size made the diffraction pattern smaller in Zmax, every time we make something bigger in here, in any of these calculations, anytime we make some feature of the object whose pattern we're calculating, then we make that feature bigger, we make things smaller in the diffraction pattern, and vice versa. And diffraction patterns are very closely related to Fourier transforms. Diffraction patterns basically are Fourier transforms. Any questions?
Professor,
Yeah.
another somewhat silly question. I don't know if it is really, but so I guess you could say that these like slit experiments are like nature's way of Fourier transforms. Are there any other natural methods of Fourier transform? Like I think on I'm on like Physics Stack Exchange, and they said the ear or a piano is another natural form of Fourier transform, but I can't really think how. So
I don't really think of a piano as a Fourier transform. The ear is a spectrum analyzer, meaning that the ear can take incoming sound waves. I mean, it's not like you've got a bunch of, in terms of what the actual vibrating air, the actual pressure waves are doing, it's not like first you got one frequency coming in, then another. The pressure waves, the pressure is just fluctuating however it's fluctuating. And the ear somehow breaks that apart so that you can simultaneously hear high pitch and low pitch. So that you can simultaneously notice the bass guitar and the violin at the same time, a child's voice and an old man's deep voice. Okay, so yeah, the ear is in some sense performing a spectral analysis. I'm a little, after seeing today's seminar, how many of you were any of you at today's seminar? There was a department seminar at 11, and we had a speaker from UCLA talking about how it is that the ear turns sound into neurological signals. I'm a little bit reluctant to use the word Fourier transform, just because if she made no other point to us, the point she made was that the ear is highly nonlinear. In some sense, we know this because sound, audible sound from just barely discernible to loud enough to damage the ear spans 120 decibels or 12 orders of magnitude. So a trillion, a factor of a trillion, and yet somehow we don't hear these things as being as different as they actually are. That scale gets flattened out. There's tremendous nonlinearity. So if I start using the word Fourier transform for it, I feel like someone who actually knows more about hearing would point out that a Fourier transform is a very linear operation and the ear is highly nonlinear. But certainly there are qualitative aspects of it in that a Fourier transform takes something and breaks it down into different frequencies, and the ear likewise does that. So I'm comfortable saying that there are aspects of it that are analogous to a Fourier transform. But to say that it's as directly a Fourier transform as a diffraction pattern is, I feel like an actual hearing expert would tear that apart. By the way, if you really want to learn about Fourier transforms in optics, there's been several editions of this book by Joseph Goodman, Fourier Optics. It is an excellent book. It goes back, the first edition was like in the 60s, and the guy's amazing. He's still writing. The most recent edition from 2017 somehow covers material on spatial light modulators and other modern technologies. So it is a very worthwhile book. we could teach a whole class on this. In fact, if we were able to offer a third optics course, I probably would teach a whole class on this. Other questions? Then we're going to end early. Enjoy your spring break. When we get back, we'll talk about lenses and the diffraction limit. On Thursday, April, what would that be, 8th, we're going to have one of our alumni coming, and she's going to be talking about her work as an optical engineer at Northrop. So definitely, well, you should always be coming to class, but in the second half of the Thursday after spring break, make sure that you don't miss that, because we're going to have someone coming about her job in the optics field. Have a good week.